Hey folks, welcome to the 10.2 video part 2. And in this video, we're going to do a very brief overview of the Taylor series, okay? This video is more about giving you a very little bit of background and some definitions and some formulas that'll help us with the questions that we're going to work on. But I have included other sources in the additional resources if you want to dive a little bit deeper into what a Taylor series is, okay? So first of all, a Taylor series, if we were to sort of think about it in the most straightforward way, is if we add up all terms in a Taylor polynomial. Okay? So we talked about Taylor polynomials in 10.1. We spent a lot of time sort of creating them, but it turns out that if you take all of these terms and then you add them all together, like literally all of them, what you get is what we call a Taylor series. Okay, so the thing that we use to approximate other functions, if we add up all those terms, it will give us a Taylor series. And in the next few sections, we're going to take a look at what we do with Taylor series and the cool applications that they have. Okay, so here's the book's definition. It says a Taylor series. So if you have a function f with a derivative of all orders at a point, so it means like you can keep taking derivatives, then the polynomial at the nth degree of this Taylor polynomial, and these are our coefficients. So our a sub n is our whatever derivative divided by n factorial, okay? We take all of these terms, and remember this sigma means that we're going to add them all up together. And we're going to add them all up together from k equals 0 all the way to k is infinity, right? And that infinity part is the part that tells us we're literally adding up every single term in the whole polynomial, okay? And so if we were to add up all the terms, we might get something like this, but I want to highlight one particular part of this, okay? Our a sub n, this actually should not be a minus, but it should be a times. Okay, so that's a little typo from your textbook. But this a sub n, that's something that we really want to focus on. So in all the questions we're going to have, I'm going to give you an a sub n. Let me only highlight that, not the minus sign. The a sub n, that is going to be our coefficient formula. Okay, so we're going to be already given the coefficient formula. And from that, we're going to want to make two choices, okay? Choice number one, we're going to want to see if this Taylor series converges at x. And the Taylor series will converge if this statement is true. And then separately, we want to look at, does this Taylor series diverge? Okay, so the Taylor series is either going to converge or diverge. It will converge if the limit exists, and it will diverge if the limit does not exist. Okay. The last piece of information that's important for us here is that the set of the numbers x for which this limit exists is what we call the interval of convergence. Okay, so our focal point in this section is going to be finding out whether the Taylor series converges or not, and if it does, what is the interval of convergence? Okay. Now, I've said a lot of words, so I kind of want to show you like what we're looking for when we're thinking about the Taylor series convergence. All right, where did that go? Okay, sorry about that. All right, so theorem number one in our book says the interval of convergence, okay? In order to find the interval of convergence, we have to determine whether, when we compare the coefficients, we end up with a number or not. That's really the gist of it. When we compare coefficients, are we ending up with a number? And if so, is that number like a regular number? Is it zero or is it infinity? Okay. So here's what we're going to be looking at. Case number one, we take our coefficient for a of n plus 1 and we compare it to the coefficient a sub n. And we're going to take our limit as n approaches infinity. Okay, so this is secretly what we were doing in part 1 of our video. We were practicing how to find that comparison between an n plus 1 and an n coefficient. Now, it turns out if we end up with a number, okay, we're going to call that number L because it doesn't really matter what the number is. It matters that it's a number and that L is not equal to 0, okay? If we get a number, it means that our radius of convergence is going to be 1 over L. Now, if we compare our coefficients, we take our a sub n, we compare it to our a sub 1, and at the end, we get 0. Okay, so maybe the degree on the bottom is bigger than the degree on the top, okay? Then it's going to turn out that the series converges for all numbers x, all the time, okay? And last case, if we have a comparison where we take our a sub n minus n plus 1 and our a sub n, and we compare them, and we take the limit as n goes to infinity, and we get an infinity. Then what that means is the series converges only at x equals a. Okay, so these are going to be the 3 cases that we look at. We'll do a couple examples in the next few videos and walk through this process. Like, what do I mean when I say we're comparing our coefficient? Okay. Now, for those of us who like sort of the step-by-step, I think the previous definitions are really great. But if you want a little bit more of a picture of what's happening, I like this diagram too. Okay. It says a lot of the same thing, but it gives it to you in a picture format. So when we say we get a number that's not 0 and our radius of convergence is 1 over L, what that means is like on this number line, there's only part of the number line between these two values where our series converges, okay? However, if we get the 0 out, maybe we've got a degree that's bigger in the denominator than the numerator, it's going to converge everywhere on the entire number line. But if we get an infinity out, then it's only going to converge at that one point. All right, so we could see here, this is just one point, whereas this is the whole number line, and this is only a specific region. Okay, so that's it for this video. When we come back, we're going to take a look at a few examples where we actually get to practice the comparison piece of this, and hopefully it'll make a little bit more sense.